So welcome back everyone. So the first thing I wanted to do today is to kind of go back and finish the discussion we had started on Kepler's time equation. And then immediately following that, we're going to dive into the beautiful world of orbital elements and specifically defining them, their meaning, and then how to use them practically in order to go from orbital elements to position and velocity in the inertial reference frame, such that we can actually initialize our two integrated blocks in the block scheme diagram I had drawn on the board a couple of lectures ago when I was talking about the importance of the first most important equation in this course, which is the two-body equation of motion minus mu times r vector over r cubed. And as I had said back then, the key thing there was to initialize the two integrated blocks. So by selecting an orbit that we want in terms of orbital elements, we'll see the process to go from those orbital elements to r and v at t equals 0, for example, and then have all the right tools to initialize the integrated blocks. Okay, but first let's talk about Kepler's time equation, which is the mean anomaly, m, equal to the eccentric anomaly minus eccentricity sine of the eccentric anomaly. As a reminder, don't forget that the eccentric anomaly in this equation has to be in radian, otherwise that equation would fall apart. But in terms of the practical use of that very important equation is that there are two things we can do with it. So let's pretend I would give you, so let's say given a true anomaly of whatever degrees or radian, the task, say, would be to find the time since perigee passage, t minus tp, okay? First practical use of that equation. Well, that's quite simple because given a true anomaly, in the first step, let's call it 1.1, is to calculate the eccentric anomaly given theta. And how to do it? Well, just apply the tan eccentric anomaly over 2 equal the square root of the ratio of eccentricities times tan true anomaly over 2, like that. Okay? So you solve that equation for the eccentric anomaly given the true anomaly. Then in the second step of this process, you go here and solve Kepler's time equation for the mean anomaly given now the eccentric anomaly that you would have calculated in step 1. I'm going to say calculate the mean anomaly now given the eccentric anomaly obtained from 1.1. We'll just solve Kepler's time equation for the mean anomaly. All right, easy peasy. And again, I'm going to write it down. Units, units, units. Very important for eccentric anomaly. Okay, and once you have the mean anomaly, well, you're pretty much done because all you have to do is to remember that the mean anomaly had been defined as the mean orbital motion n times time since perigee passage t minus tp. So if this is what you're looking for, all you have to do is do m over n, and that will give you your answer, t minus tp. Okay? Three-step process to calculate the time since perigee passage at a given true anomaly. Okay? That is to say, if this is M1, and I were to pick a random position vector where the spacecraft is currently, if I say, okay, my true anomaly is equal to 110 degrees, find how long did it take the spacecraft to fly from the perigee at Tp all the way to here. So what is the time elapsed between those 2 points essentially is the time since perigee passage. Okay, this is what this procedure gives you. Given T minus Tp, given through anomaly, find T minus Tp. Okay, pretty straightforward. It's just a matter of plugging and playing with the equations. So let's have a look at the inverse problem, which brings us to the second use of Kepler's time equation. So here in the second use, we're going to say, now given T minus Tp, find the true anomaly. So that is to say that I could ask you, okay, the spacecraft is 20 minutes away from the perigee, that is T minus Tp. What is the corresponding true anomaly at that specific instant? Well, now, all you have to do is to go back to Kepler's time equation and calculate your mean anomaly first. So given T minus Tp, so we just say M is equal to the mean orbital motion times the time since perigee passage. That first step is pretty easy. And then in 2.2, given the mean anomaly, you have to solve that equation for the eccentric anomaly. Solve Kepler's time equation for eccentric anomaly given the mean anomaly. Is that easy? No, this is quite difficult because that equation, unfortunately, cannot be solved directly for the eccentric anomaly given the mean anomaly. There's no way you can do it directly. The only way to solve that equation for big E, the eccentric anomaly, is to iterate, okay? So here I'm going to say iteration or iterations, because you have to iterate more than once. I'll show you the process right after. And then finally you obtain your eccentric anomaly after X number of iterations. And then in 2.3, what you do is that you just calculate your true anomaly using tan theta over 2 equal the square root of the ratio. Always forget if it's 1 minus E over 1 plus E or the other way around. I'll let you figure this out based on your handwritten notes a couple of lectures ago. Tan theta over 2 equal this ratio times tan eccentric anomaly over 2, where you had solved the eccentric anomaly in that second step here. Okay? So let's have a look at how can we iterate to solve for the eccentric anomaly. That equation is known as a transcendental equation. And this is why it cannot be solved directly for the unknown on this right-hand side here. Okay? So, iterative procedure to solve Kepler's time equation given the mean anomaly. Okay, so the iterative procedure goes as follows. And by the way, when I say solve Kepler's time equation, what I mean by that is solve for the eccentric anomaly, okay, obviously. So this is an iterative procedure, so the next iteration on your eccentric anomaly will be equal to your previous iteration minus the previous iteration minus eccentricity sine your previous iteration minus the mean anomaly, which you have from before, and all of this divided by 1 plus, minus E cos the previous value of the eccentric anomaly. And you repeat that for all. This is a symbol that means for all in mathematics. For all I equal to 0 all the way to n iteration, where n can be 3 iterations if you do the process by hand. If you have access to a MATLAB software through a computer, then n, it's up to you. Just create a for loop and you iterate in software all the way to 100 or something like that. But in practice, we like to stop the iteration. You want to say stop iteration whenever the difference between two values obtained from two different iterations is less than threshold, okay? Whenever E I plus 1 minus the previous value from the previous iteration is less or equal than some threshold, typically determined by the professor, i.e. me, okay? Or again, in software, just iterate for as long as you want, 100 iterations, and you're going to get to a pretty accurate value for the eccentric anomaly. Now, that's kind of easy to understand, but the question is, how am I going to start the first iteration if I need the previous value, right? Because to calculate the next value, you need the previous one. Well, where do you start? The starting point is E naught, so the first value for the eccentric anomaly. So we're going to say start iterations with E naught, and then the first good guess would be to initialize it to be equal to the mean anomaly, okay? Again, the mean anomaly had been solved previously because you're here, so you had calculated mean anomaly, and then you plug it into E naught, and then based on that you calculate E1, which will be equal to your E naught minus E naught minus E sine E naught minus M, this divided by 1 minus E cos E naught. That's going to give you the next value for the iterative process. And then you keep going. Now that you've obtained E1, you're looking for E2, the second value of the iterations, which is now based on the previous one, which happens to be E1, like that. 1 minus E cos E1, and you keep going for as long as you have the energy or the patience to do it, okay? Again, in an exam, I will let you know when to stop the iterative procedure. So I will say stop at E4 or E3. But in an assignment or a problem, it's really up to you because you have access to MATLAB or any kind of software you want to use. So just keep going for as long as you wish, okay? So these are the two uses of Kepler's time equation. So given the time since perigee passage, how can you find the true anomaly? Or vice versa, given the true anomaly, what does that translate into the time since perigee passage? Okay? So let's dive into something else, which is quite fun actually. Well, I think it is fun. Maybe you won't think it's fun, but that's another story. It's all about orbital elements, okay? Because again, we're engineers and we like practical applications of things. And again, one practical application of the two-body equation of motion is to use it in a simulator. Hopefully by now you have been made comfortable with MATLAB Simulink through 3600 systems and simulations. So this is a block in Simulink that you can call dynamics, which is going to calculate the XYZ component of the acceleration, the vectors, as seen in some inertial reference frame for your spacecraft. Okay, so these are R double dot in an inertial reference frame that we will define in a moment. But remembering that this is a 3x1 column matrix. Okay, so this contains R X I R Y I R Z I in terms of acceleration components. Okay? How can we get that? Two-body equations of motion minus mu. Our vector in practice in the numerical simulator, because we don't play with vector objects, but we play with components of vectors. So we're going to say I'm going to take the X, Y, Z components in the inertial reference frame over the Euclidean norm of this 3x1 column matrix, and then I'm going to cube it like that. This is going to give us the inertial acceleration, x, y, z. From there, we will integrate once to get the x, y, z component of the speed of the velocity vector in the inertial reference frame, which we can also integrate again. 1 over s is your integrated block to get the position x, y, z in some inertial reference frame. Take this and feed it back into this dynamical block. So the input is only this. Mu is a constant. So inside this block, you just multiply a constant with the x, y, z component of this 3x1 array in Simulink. And then you're going to divide this with the x component square plus y component square plus the z component square, square root of all that. And then you're going to cube the result, and that's going to become your denominator. And then you close the loop like that. So the entire process here is pretty straightforward. This is how we simulate any dynamical equations of motion, whether it is for the orbital dynamics or whether it is for the attitude dynamics, which you will see in Aero 4440, the subsequent course to this one. But the key thing here again, and I've talked about it in the past, is how can we initialize those two blocks? Well, here we need the initial velocity. So R, I, component, velocity, at t equals 0. And here, we're going to need the initial position, x, y, z, defined in some inertial reference frame, at t equals 0 like that. While specifying those 6 scalars, because this is x, y, z velocity, x, y, z position. So we have 6 scalars to define. To uniquely define an orbit, do we want to generate an elliptical orbit at the end of the day? Or are we interested into generating or simulating a circular orbit? Things like that. At which inclination do we want our orbit with respect to the equatorial plane of the Earth? Well, all of this is solely dictated through these initial conditions. But it's not very intuitive to use those initial conditions. Okay, so instead we use a tool or a much more intuitive way to define orbits, and that is through the use of 6 orbital elements. Those 6 orbital elements are 6 scalars that define the size of the orbit, the shape of the orbit, defines the orientation of the orbital plane in 3D with respect to some inertial reference frame, and also define the orientation of the orbit within the orbital plane. And the last orbital element is used to locate the spacecraft along the orbit. It could be the true anomaly, but here we're going to use the time of perigee passage instead as a 6th orbital element, okay? But we'll get to that in a second. So we use those 6 orbital elements to very easily and intuitively specify our orbit we'd like to visualize, say, MATLAB Simulink. Based on those 6 orbital elements, we will then convert them at a specified time. That specified time will be t equals 0, such that we obtain position velocity at t equals 0 and position at t equals 0. Okay, and then based on the output of this process, then we're going to feed that to initialize our integrator blocks. So next up, I'd like to define those orbital elements to you, explain what they are, their meaning, and then I'm going to see this process, how to turn those 6 easily defined orbital elements for a given orbit into something that we can use to initialize the 2 integrator blocks in MATLAB Simulink that will ultimately achieve a 3D orbit that you'll be able to visualize, okay? So first, we're going to have a look at the 6 classical orbital elements that we're going to use, and then the process to turn them into position velocity at some arbitrary time. For this process here, just keep in mind that that specific time will be t equals 0 seconds, because those are used as initial conditions or as conditions at t equals 0. Okay? So that's going to be the bulk of today's work. But actually, before we can define the 6 orbital elements, we have to specify what is our reference. I talked about defining the orientation of the orbital plane in 3 dimensions. Well, you know by now that defining an orientation is relative to something, okay? That something, in our case, is a reference frame, obviously, that we're going to call the Earth Inertial Reference Frame. And then we'll see how to go from there. So 2.6 is all about orbital elements. Okay. So in 2.6.1, because orbital elements are used to define the shape, size, orientation of the orbit, and position of the spacecraft along the orbit, we need to define what is our reference with which we're going to determine the orientation of the orbit. Okay? And that reference frame is known as the Earth centered inertial reference frame. This reference frame is going to be used tremendously in this course and in the follow-up course, Aero 4540. So because it is such a common reference frame in spacecraft applications, it actually has an acronym, which is ECI, Earth-Centered Inertial Reference Frame. So let's see how this reference frame is positioned and aligned with respect to obviously the Earth, okay? So if this is the Earth, if like that, with its equator here, and ultimately an equatorial plane that goes through the equator, like that. The Earth also has a polar spin axis, which is the axis of rotation of the Earth, which means that this is the axis about which the Earth spins by at a rate of 2 pi per day. Okay, 2 pi per day. That. So the equator. Well, our ECI reference frame, as the name implies here, has its origin right at the center of the Earth. This is our origin. So origin. At center of the Earth, right here. Okay? It has its x-axis, x or x unit vector. Remember our discussion about unit vectors in chapter 1. So it's x unit vector is pointing towards Aries. Is there an A? X. It's not in the lecture notes, so I'll let you figure this out on your own, the spelling of this specific star. So that is a star, okay, out there, towards which our axis, our x-axis points to. So this is IX unit vector. So for to use the same nomenclature, I'm going to say IX unit vector. So this vector goes from the center of the Earth at the origin of the ECI reference frame and has its x-axis pointing at a given star in the sky. It has its z-axis in the direction of the spin axis of the Earth. So that would be IZ, pointing towards the North Pole, like that. So IZ along spin axis of the Earth. And then it means that IY, the y unit vector of this particular reference frame, is along the equator, IY, along the equator, so in the equatorial plane essentially, and is given by the cross product of IZ with IX. Okay? So whenever you talk about any reference frames, you can also only define 2 out of the 3 unit vectors, and the third one is always obtained by the cross product of the other 2, which is what we did here. We specifically define the orientation of IX, given that it's pointing at a specific star, IZ pointing in a very specific direction, like that, and IY is just a cross product of those 2, okay? IZ cross product IX gives you IY towards the right of the board. Happens to be in the equatorial plane. Did I forget something? Oh yeah, one thing to notice here is that because this axis here, this unit vector Ix, is always pointing at the same star in the sky, it means that this reference frame is not physically attached to the Earth, okay? Because otherwise, as the Earth would rotate, Ix would rotate with it and lose sight of the star it's supposed to be pointing to. So if I'm the reference frame and I'm pointing at a star, it means that regardless of the rotation of the Earth about Iz, which is up through my head, Ix is always pointing in the same spot, okay? So I'm going to say that ECI does not rotate with the Earth. This is key, okay? Now, but wait, isn't that supposed to be an inertial reference frame? Meaning that it's not supposed to move, right? But how come? Because we know that the Earth does move, right? The Earth travels around the sun. This is the sun. So if you look at the Earth, motion around the sun, something like that. So this is ECI. ECI. ECI reference frame, always centered in the center of the Earth. Doesn't that mean that the ECI reference frame moves? Yes, it does move, but the orientation of the frame with respect to the Earth, which is about which our spacecraft is rotating, is not relevant. Say, okay, but then I don't understand. If that reference frame is supposed to always be pointing at the same star, which is way out there, how come this reference frame then is not rotating with respect to the Earth to make sure that this vector points at the same star out there? Shouldn't it be rotated like that here and then moving upward here to ensure that we always point at the same star? The answer is yes. But because this star is so far away, way out there, that motion of ECI with respect to the Earth to ensure that Ix unit vector always points at that star is very minimal. So although ECI is not a truly inertial reference frame, for all practical purposes, we will nevertheless consider that it is an inertial reference frame, okay? And this is not unique to us. All textbooks in spacecraft dynamics do the same. Researchers do the same in their journal papers and things like that. So this is a very common assumption for any spacecraft-related dynamics and control work, okay? So it's not something I came up with. So this is the inertial reference frame from which we will measure then the orientation of the orbit, its alignment, and things like that, okay? So this is our reference from which we'll then define the 6 orbital elements. Okay, and that will be in 2.6.2, where we'll formally define our 6 classical orbital elements. The reason why I specified that we are talking about the classical set of orbital elements in this course is because there are many sets of orbital elements that exist out there, yet for the purpose of our course, the classical ones will fit the bill, okay? All right. So we have 6 orbital elements. Turns out you already know 3 of them, okay? Because the first one defines the size of the orbit. And surprise, surprise, this is our semi-major axis, okay? The smaller the semi-major axis, the smaller the orbit. The larger the semi-major axis, well then the larger the orbit, obviously. So this is an orbital element that defines the size of our orbit. There's also the shape of the orbit. Are we talking about a circular orbit? Are we talking about a slightly elliptical orbit or a highly elliptical orbit? Or even a parabolic orbit, which is open-ended, or a hyperbolic orbit? All of those shapes are defined by the eccentricity. Defines the shape of the orbit. Okay, this is E. Now, the three next orbital elements are there to define the orientation of the orbit in 3D space. So we have two that will both define the orientation of the orbital plane. Well, again, orientation with respect to what? Well, with respect to the ECI reference frame, which is again our reference from which we will define all the different angles in 3D space. So define the orientation of the orbital plane with respect to the Earth-centered inertial reference frame we just looked at. Those two angles are the right ascension of ascending node, which is capital omega, and the inclination angle I. The fifth one here is used to then define the orientation of the orbit itself within the orbital plane. Okay? Because those two only define a plane. Pretend that that plane is the whiteboard. Well, within this whiteboard, for a given size of the orbit, its shape, and the orientation of the board, we could have that orbit oriented like that, oriented like this, and so on and so on. So we need to then define the orientation of our orbit, which we know the size, the shape, the orientation of the board, but we still need to define again the orientation of that orbit within the board. And this is what the fifth one does for us. That one is defined by omega, okay, known as the argument of perigee. Let me write down the names next to the orbital elements. A, no big news, semi-major axis. E is our eccentricity, which define the conic section, essentially. So is it a circle, an ellipse, a parabola, a hyperbola? And as we've seen in the past, this is only dictated by the value of E. If E is equal to 0, then we know that our orbit is going to be perfectly circular. If it's larger than 0 yet smaller than 1, this is going to be an elliptical orbit. Equal to 1 parabolic orbit, and larger than 1 hyperbolic orbit. Okay. This one here, capital omega, is known as the right ascension. With a C perhaps. Oh, with T. Is it a C or a T? That's an S. right? Ascension of ascending node. That's quite a mouthful. So to make our life easier, we'll simply abbreviate it as RAAN, right? Ascension of ascending node, and call it RAAN. So the RAAN is the third orbital element. I is our inclination with a T, inclination. Small omega is our argument of perigee. And with those 5 first orbital elements, we have completely defined the shape, the size, and the orientation in 3D space of the orbit. Yet we need a 6th one that will define the position of our spacecraft. Okay? Inside the orbit, position of SC along the orbit. 2 common orbital elements to do that are time of perigee passage or the true anomaly. Okay? Within this course, we're going to stick with the original formulation of the classical set of orbital elements, which uses time of perigee passage to define the position of the spacecraft along the orbit. So this is a time-dependent orbital element here. All right? But you can pick up a textbook and they will use true anomaly and so on, but this is fine. I'm going to stick with TP nonetheless here. All right, so those are the 6 orbital elements. Let me then show you what some of them mean in terms of 3-dimensional orientation of the orbit. I would highly suggest that at this point you pick up a new piece of paper and draw it in big and dedicate that single page to the following figure, because it's going to get cluttered with a bunch of angles and lines, and it's all in 3D, so it can get confusing very rapidly. So let's have a look at the Earth. Blue. Does it look like a sphere, like a circle? That's what it's saying. Let me do it again. Hopefully you can start to see the Earth. Yeah, it's pretty good. Let's also draw our orbit in, let's say, red. An arbitrary orbit around the Earth, like that. Not too bad. Not too bad. All right, so semi-major axis defines, again, the size of our orbit. Eccentricity defines the shape. Is the red patch a circle or an ellipse around the Earth? That's easy peasy. Now, another one which is easy to visualize is the inclination, because the inclination happens to be the angle between the equatorial plane or the equator and the orbit. Okay? So inclination is this angle right there between the equator and the orbit. This is the equator. As a side note, whenever I is less than pi over 2, we're going to call the orbit we get a prograde orbit whenever I is larger than pi over 2. We're going to get what's known as a retrograde orbit. If I is exactly equal to or close to pi over 2, then the orbit will be referred to as a polar orbit, because as you can see, would mean that this angle would get to 90 degrees, and then the orbit would go from the South Pole all the way to the North Pole and so on. And lastly, if the inclination is equal to or very close to 0, then we get what's known as an equatorial orbit, flat along the equator. Okay? So this one defines that angle of the orbital plane. Then we also have RAAN, right ascension of ascending node. This is the angle that is defined between IX, which points at some star, Aries, in the direction of the vernal equinox. Vernal equinox. I'm not too good at astronomy, but I think the vernal equinox is denoted by that symbol. Okay? It points at a star essentially, which is fixed in the sky. And so this is the angle between that unit vector, Ix, and the line along the equator that goes through the point where the orbit or the orbital plane meets the equator. Okay? This is known as the line of node. So if you think about the horizontal plane here, the plane of my sheet of paper as being the equatorial plane, and if you have an orbit that is inclined with respect to this plane, say like this. So imagine two planes intersecting with each other along a line. Draw that line along the equatorial plane, and this is the line you will get. Okay? The other portion of this line will be going towards where the orbit goes down along the equator, because the equator obviously goes all around the Earth. Like that. Not sure if it's getting too cluttered, but you also have, yeah, you see the orbital plane in red, and you have the equatorial plane in blue. Where those two planes meet, you can draw a line, and you have to look at the direction where the orbit goes from the southern hemisphere up the northern hemisphere of the Earth, and that vector from the center of the Earth into that direction is the line of ascending node, okay, capital N, because this point here, where the orbit goes from south to north, is known as the ascending node. On the other side, when the spacecraft goes down along the orbit and goes from the northern hemisphere down to the southern hemisphere, that point here along that line of nodes is known as the descending node. All right? So, all this to say that RAAN is the angle between Ix and the unit vector that defines the ascending node direction. So it is this angle measured in the equatorial plane. I'm going to say angle between IX and unit vector pointing at the ascending node, that point here, when you go from south to north along the orbit. I'm going to say in parentheses that this angle is in the equatorial plane. All right? And the reason why I'm specifying it is because it gets very cluttered and it might be difficult to visualize this in 3D, especially with my superior drawing skills, right? Yes. So now we've defined the size, the shape, and the orientation in 3D space of our equatorial plane through the inclination and radian. But now we need to define, again, the orientation of our orbit in the equatorial plane, meaning that we need to define the location of our perigee. Is the perigee here, 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 or here? I don't know, because we haven't defined that yet. So to do that, we need to use the argument of perigee. Okay, that works. Which is omega, which is the angle between the unit vector pointing in the direction of the ascending node, or capital N, and the perigee of the orbit. Let's pretend the perigee is over there, meaning that this point is the closest to the center of the Earth, although it's difficult to picture in this very random orbit that I've drawn in red, such that you have your eccentricity vector pointing at this specific point, as we saw in the past. So again, the argument of perigee locates where the eccentricity vector points, or alternatively locates where the perigee is within the orbital plane. So this is this angle here, omega, between N and eccentricity vector that points at the perigee. So it essentially locates the perigee, or mathematically this is the angle between N and the eccentricity vector E. And finally, the time of perigee passage tells us what is the time at which the spacecraft was over the perigee. Okay? TP. With respect to what? With respect to t equals 0. Because perhaps we decide to initialize our spacecraft around here, or over Canada, or directly at the perigee, at which point we could say that TP is equal to 0, or here, or things like that, okay? So TP is there to, again, give us an information about the location of the spacecraft time-wise along the orbit. Nice. That wasn't too bad. By the way, I would highly recommend that if you're not too sure about my really beautiful 3D drawing here, go to the internet and Google Orbital Elements, and you'll see a bunch of fantastic 3D pictures on the web. And that could really help you try to visualize the 3D orientations of things here, okay? But I think that I did a fair attempt here. I did the best I could. All right. So where are we now? Orbital Elements H15. Okay. So the last thing I want to do today is go with you over the procedure that we need to convert those 6 orbital elements into position, velocity, x, y, z components in the ECI reference frame at some time, say t equals 0, such that we could use those 6 new scalars calculated from the 6 orbital elements and use those into the initializing blocks in our Simulink diagram, which is used to simulate an orbit in MATLAB Simulink. Okay? And the process needs to invoke a new reference frame. That's great because I know by now that you love reference frames, right? You like them so much that I'm gonna have a look at another one here known as the perifocal reference frame. And this section is practically used to convert 6 orbital elements, OEs, to position and velocity in our ECI reference frame, like that, at some time of your choice, at some t, which is up to you to determine. Based on the 6 orbital elements, you can determine position velocity at any time. Is it at t equals 0 to use to initialize the integrated blocks? Is it at t equal 100 seconds? Is it at t equal 2000 seconds? It's really up to you. It's going to be a plug and play procedure, okay? Up to you. I'm going to say you're going to set t equals 0 to ultimately find if that's what you want. That's some random position velocity matrices in ECI, but specifically at t equals 0, and that is to initialize the 1 over s blocks in Simulink. Okay? Well, that is a big title for subsection. The lecture notes only use perifocal reference frame, which is a lot cleaner, but here I just want to give you kind of deeper understanding of that single section. All right, so that is the purpose here. That is our objective. It's always good to keep the objective of a subsection in mind, because when I start deriving equations, I can go on for a long time, and if you lose sight of why we derive equations, then it could get pretty boring very quickly, okay? So perifocal reference frame. But the first thing actually we need to do in the procedure to go from orbital elements to R and V without even using that perifocal reference frame is to use Kepler's time equation, which is T or N times T minus TP equal eccentric anomaly minus eccentricity sine eccentric anomaly. Okay, so TP is given to you because you go from the 6 orbital elements to R and V. So this is given. It's one of the 6 orbital elements. Eccentricity is given to you. That makes you happy. That makes you happy. This T is up to you. Do you want to ultimately find R and V at t equals 0? If so, just plug t equals 0. You want R and V at t equal 500 seconds? If that's the case, feel free to plug 500 seconds for t in that equation, okay? So up to you. That makes you happy as well. N is a function, a nonlinear function of the semi-major axis and the gravitational parameter mu only, right? That's a constant. A is given to you, and that makes you happy, because then you can easily calculate N. So if you look at that, the only unknown in that equation is the eccentric anomaly, capital E. So the first step of going from orbital elements to R and V in ECI is to solve Kepler's time equation for the eccentric anomaly. And thankfully by now, you know how to do it. And that is through the iterative procedure to find the eccentric anomaly. And again, for doing it, I'm going to start the iteration procedure with the first assumption or the first value of E. I'm going to set it equal to the mean anomaly or equal to N times T minus TP, which you know up front. Again, because TP is given to you, T, it's up to you to decide, and N you calculate from the semi-major axis, which is given to you. So in other words, you have everything you need to start off and calculate the eccentric anomaly. First step of the entire process. Then second step, what you want is to calculate the true anomaly based on the eccentric anomaly. And it turns out we also have a relationship to do it. Which is, I'm going to write it properly this time, with the actual things that go there. So 1 plus E over 1 minus E, square root of that, and then tan of the eccentric anomaly you've just found previously. And you solve that equation for the true anomaly. That's what you want. Next, once you have the true anomaly, you want to calculate the distance between the spacecraft and the planet using the orbit equation. And we're going to use the version that uses the semi-major axis in the eccentricity for the numerator, because those two things are given to you. Over 1 plus E cos true anomaly that you found in the first step. Now keep in mind that that here is valid for the time you've specified here. Okay? So for a given time at which you want to solve R and V at the end of the entire procedure, you're going to get a different true anomaly. And then you're going to get a different R, and then it's going to snowball till the end to give you a very specific set of position velocity components in ECI. So everything is based on the characteristics of the orbit as well as the time at which you want to solve R and V in ECI. Okay, I cannot stress that enough. It seems like a very intuitive way of looking at this procedure. You set the time at which you want to solve R and V. Yet, I'd say the quarter up to close to half of the students in the midterm screw that up for some reason. So make sure, if you're not too sure what's the objective of this procedure or how things are connected to time, and specifically the time at which you want to solve the answers for, then feel free to rewatch this clip or this video as many times as you want, okay? All this to say that set the time, get the associated true anomaly, from which you get the associated orbital distance, or the distance between M1 and M2. And then this is where you need to use the perifocal reference frame to keep going with the procedure. So let's talk about the perifocal reference frame, because now we need to use it again to solve ultimately R and V and ECI. So the perifocal reference frame is organized like that. So this is an elliptical orbit. With M1, the Earth, Well, the perifocal reference frame, which is referred to as calligraphic capital F subscript P for perifocal, has its origin at the center of the Earth, just like ECI, if you remember. But this time has its x unit vector along the eccentricity vector, or in other words, pointing in the perigee. So px unit vector points at the perigee, which is the same thing as saying along the eccentricity vector E. Has its z unit vector out of the orbital plane and normal to the orbital plane, essentially. So I'm going to say normal to the orbital plane, which in this drawing happens to be the plane of the whiteboard, because the orbit is drawn in this plane. So PZ will be out of the board, pointing directly towards you. This is PZ. So perpendicular to the orbital plane in the direction of H. What is H again? H is the specific orbital angular momentum vector, which happens to also be pointing in the same direction because H is always perpendicular to the orbital plane. And this is how we have been able to infer the fact that the orbital plane was inertially fixed, because H dot was equal to the null vector, right? Go back to fundamental integrals if you don't remember or don't understand what I'm talking about, but this is what it means. And lastly, because I've defined two of the three unit vectors, I can simply obtain Py as a cross product of Z and X. So Pz cross product Px. Which would give you a vector inside the orbital plane, 90 degrees from Px, and obviously 90 degrees from Pz2. All right? I'm not going to attempt to draw a perpendicular symbol between y and z. I'll just screw that up. Okay? Or maybe I could go like that and like this. All right? You could also write, because Px is in the direction of the eccentricity vector, and because Px is a unit vector, you could write that Px vector is the eccentricity vector over its norm to make it a unit vector. And you could also say that because Pz is in the same direction as H vector, yet because Pz is a unit vector, what you do is that you can write Pz equal to H, same direction, yet different magnitude, because Pz is unit vector. So you take H vector and you define by its norm, you get a unit vector in the direction of H, okay? This is how you can mathematically obtain those two unit vectors, and then for the third one is the cross product of the first two. Great. How does that help us? Well, it's very helpful because now that we have, oh, by the way, I should have said it before, but this reference frame, perifocal reference frame, does not move, okay? Because this is actually, the orientation of this frame is actually independent of the spacecraft position along the orbit. It will never change, okay? Now again, how is that helpful? Well, now because if you go back to what we had obtained from the 6 orbital elements previously, well, we have calculated r, the distance between the planet and the spacecraft, as well as our true anomaly. At what time? At the time you have specified in the first step. It's up to you through the determination of t, or the selection of, not t, but t, the selection of t. This is up to you as a designer to select t. Okay? So what it means is that you could then write completely the position vector inside this perifocal reference frame in terms of components. How? Well, by using the fact that the perifocal reference frame has 2 of its 3 unit vectors inside the orbital plane. Correct? Go back to your orbit. M1, Px, unit vector, Py, unit vector, and Z out of the board towards you, which means that you can completely describe the position of the spacecraft inside the orbital plane only using those 2 directions. The spacecraft will never be out of the orbital plane. The spacecraft always evolves along the orbit, which lies inside the orbital plane. Okay? Which means that, for example, if the spacecraft happens to be here along its red orbit inside the orbital plane, which is the plane of the board, it means that our vector, the components of R, has characterized or has measured in that specific reference frame, could be completely determined along X and Y only. So in other words, the R vector in terms of components will never have a PZ component. It's just impossible. So 0 for the Z component of your position vector as seen in the perifocal reference frame. All right? Well, what about X and Y? Well, if you know, or if you remember that Px points along the eccentricity vector, and that here you have the true anomaly angle between eccentricity and therefore between Px and your position vector, you can simply use trigonometry to write that the x component will be equal to the length of your vector, which is r, cos true anomaly, and here r sine true anomaly. Okay? Where, by the way, this fits into expressing this position vector in the perifocal reference frame, like that, as we've done extensively in chapter 1. Okay, this is how to express a vector in a specific reference frame in terms of its x, y, z component. Well, it turns out in the perifocal reference frame, the x, y, z components are r cos theta, r sine theta, and 0, like that. And that's why it is useful to use the perifocal reference frame, because in that reference frame, all we have to deal with are 2 components. Because again, the spacecraft will never have a component out of the board. The spacecraft has to always evolve along the orbit, which lies in the orbital plane. Nice. This is for RP. What about the velocity vector seen in the perifocal reference frame? Or in other words, what would be the x, y, z components of your velocity vector in that perifocal reference frame? And what would be Vp equal to? Well, that's not too big of a deal because we just obtained Rp. So all you have to do is to do the time derivative, inertial time derivative of this guy, and then apply the chain rule to then write that this is going to be r dot cos theta minus r sine theta times theta dot. This is just applying the chain rule to this expression. And chain rule in terms of derivation applied to r sine theta will give me derivative of the first term, which is r dot, times the second one as it is, plus the first term, r, times the time derivative of sine theta, which is cos theta. And because this is a trig function, you also need to do the time derivative of what you had inside the trig, which is theta, which then becomes theta dot. And 0 stays 0. Boom! You're done. You went from 6 orbital elements to position and velocity, x, y, z components. At what time? At the time you've specified earlier. Was it at t equals 0, such that these correspond now to our p naught and vp naught? Or is it at t equal 200 seconds? And so on and so on. It's really up to you. I know I sound like a broken record, but I really want you to understand what we're doing and how we do it, okay? But no, we're not done. Well, why? We have x, y, z position, x, y, z velocity at the time we wanted. Yes, we do, but not in the right reference frame. Those 6 quantities obtained from the 6 classical orbital elements are obtained in the perifocal reference frame. That wasn't the objective. The objective up front was to obtain Ri and Vi, or x, y, z components of the position vector seen not from the perifocal reference frame perspective, but from the ECI perspective, as well as components, x, y, z components of the velocity vector seen in the ECI reference frame. 6 orbital elements to those things. Yet, what we have now is almost the end product that we're after, but we have them in the wrong reference frame. Gee, what do we do about it? We have components in a given reference frame, yet we want them in another reference frame. Do we have the tool to transfer components of a vector in a reference frame up to another reference frame? The answer is yes, obviously. And how we do it practically? Well, we do it with the use of rotation matrices. Wow, chapter 1 coming back to haunt us again. Yes, and that's why I said that chapter 1 was the most fundamental building block of the entire course. If you don't know what a rotation matrix is at this point, you're in trouble, okay? Because that was a foundational block of the entire course. We are just playing with the same blocks in different ways and using the new tools we have learned in chapter 1. So if you don't know the tools you have, and furthermore, if you don't know how to use them, you're going to have a hard time in this course, okay? So now the idea is to go from position vector in perifocal and velocity vector in perifocal to position, velocity vector, but seen in the ECI reference frame. Not a big deal, because we know our chapter 1 very well now. So all we have to do is to apply a rotation matrix that takes us from perifocal all the way to ECI. We apply it to both the position and the velocity components, like that. So the trick is to now determine this rotation matrix, CIP, or the rotation matrix that gives the orientation of the ECI reference frame with respect to the perifocal. Okay, this is what CIP means. Orientation of ECI with respect to the perifocal reference frame. This, to me, is not that intuitive to calculate. Maybe it is to you. To me, I find that defining the orientation of perifocal with respect to ECI is a lot more intuitive. So to me, I prefer to calculate CPI, which is the inverse of this, right? Because that would be the orientation of perifocal with respect to ECI. This is what CPI denotes. But you know, you can easily get it by taking the inverse of CIP, but we don't like taking the inverse of the 3 by 3 matrix. Turns out we're fortunate because the inverse of rotation matrix is equal to its transpose. Remember the trick I gave you in chapter 1? That taking the transpose of a rotation matrix only flips the subscript around, the subscripts around. Well, this is what we're going to take here. This is what we're going to do. But just the other way around, because I need CIP, but to me it is easier to calculate it. So because I need CIP in the end, this is the result I need to keep moving forward with the procedure, but I prefer to calculate CPI, and all I'll do is take the transpose of CPI, and the job will be pretty much over. Okay? So how do we get CPI? Well, because you probably have never done it yourself, to define a rotation sequence just based on the sheer geometry of the problem and looking in 3D at all the angles involved, I'm going to give it to you. So I'm going to say that it can be shown, and I would highly encourage you to look at the 3-dimensional geometry of perifocal with respect to ECI and try to see if you could determine it yourself. But here I'm going to give it to you. It can be shown that perifocal is obtained from ECI through the sequence three, 1, 3. Meaning this is a rotation about the Z unit vector first, followed by a rotation about the X unit vector second, and lastly, a rotation about the Z unit vector again. And the angle involved was 313 with angles rad, inclination, and argument of perigee omega, respectively. Okay, so the first rotation you do is a rotation about IZ through this angle. Then you rotate about the X unit vector of the intermediate reference frame that you've obtained after the first one through an angle of I equal to the inclination. And then lastly, you rotate about the Z unit vector of the second intermediate reference frame that you've obtained after the second rotation, and you do that last rotation through an angle which is equal to the argument of perigee to ultimately obtain your perifocal reference frame. Okay? So based on the wording here, this is very important that you can translate that into a sequence of principal rotations back to back. So I'm going to do it for you. So just on the wording, I know that we're talking about FP, or perifocal, being obtained from ECI. So that means I'm looking at CPI. Okay? where I is my initial reference frame, if you will, and P is the final reference frame. So CPI, the sequence is 313 with those angles, but I remember that the prof told me that I needed to flip the order backwards to get the order of the principal rotation matrices. And we had actually showed it on the board through the 3-2-1 rotation sequence, and you've been able to appreciate the fact that we do indeed need to flip the physical rotation sequence to get the order with which you multiply the principal rotations, okay? So this is the first physical rotation, second rotation, and third rotation. So I'm going to flip the order backward and write C3 through an angle argument of perigee, starting here, and then I'm moving to here, which is C1 through an angle inclination. And finally, I'm going to multiply all this with C3 through an angle Rayyan, like this, okay? So this is the first physical rotation to take place, the second one, and the last one. And the order told me, or the sequence told me, that the first one was this, second, third, first, second, third, in that order. Don't mess up the order, so don't write C3 Rayyan, C1 inclination, and C3 argument of perigee. You're gonna get the wrong result, and you're gonna lose 50% out of that question in an exam right away, right up from the get-go, okay? So pay attention to those details, they are fundamental. All right. Oh boy. C3 times C1 times C3, which is the same as CZ, CX, CZ, by the way, as we've discussed in the past. Turns out we're fortunate because I gave you the definition of CZ or C3. I also gave you the definition of C1 or CX. And yeah, all you have to do is to apply those with the appropriate angles, okay? So this is a multiplication of 3 by 3 matrices. Your CZ has the 1 third row, third column with zeros over there. And then you have cosine, minus sine, and cos of your omega. Okay. Say omega over there with trig functions. I don't know on top of my head. And then you have the C1, which has the 1 on the first row, first column, and the rest being filled with sine and cos of your inclination angle. So I'm just going to write function of. Just remember that you have to go back to the lecture note definitions and use the appropriate trig functions here for those 4 terms. And the last one is similar to the first one, so 0, 0, 1, 0, 0, cosine minus sine cos of your Rayyan inside this matrix. Hopefully you're good at linear algebra because you'll have to multiply all of this by hand, and you're going to get a result for CPI. That result will have to be transposed to get CIP, okay? Sorry, CIP is the transpose of that result. Well, once you have CPI, just flip the rows with the columns and you're going to get essentially CIP. This is what a transpose operator does. And once you have CIP, you're pretty much done with the process. By the way, for CPI, I gave you, or for CIP, I gave you the answer in the lecture notes. This is equation 2.92. I'm going to say C, which is a symbol of an I, which I thought would have been faster than writing C, which is only 3 letters, but turns out that drawing an I is a bit longer, so that's a nonsense. But I'm going to say C, equation 2.92, which gives you the result of CIP. So I would highly recommend that you try this out on your own to confirm that you are indeed able to multiply three 3x3 matrices together and then take the transpose of that to get CIP, okay? Because again, if you can't do that simple operation, you're going to have a hard time in the rest of the course, and especially during exams. Okay. And once you have CIP, because you had previously determined the value for RP and VP, remember RP was your simple R cos theta, R sine theta, and 0 along X, Y, Z direction of perifocal. Well, all you do is that you multiply it with CIP to finally get what you were after half an hour ago, which was components of your position vector in ECI and components of your velocity vector in ECI as well, just like that. If you had chosen t equal to 0 to initiate the entire procedure, then what you get is those things that you can then use to initialize or set the values at t equals 0, the integrated blocks in dynamics that will allow you to generate a three-dimensional orbit. Okay? So this is how you go from orbital elements to position velocity in the inertial reference frame and how to use it practically to simulate an orbit in MATLAB Simulink. I think that's enough for this one. We covered a lot. Went back first and talked about the two practical applications of Kepler's time equation, which were to find time since perigee passage given a true anomaly value, or the other way around. And one of those two needed to involve an iterative procedure we talked about. And then we defined the inertial reference frame that we're going to use throughout the course, which is the Earth-centered inertial reference frame, or ECI for short, that has its origin at the center of the Earth, its x-unit vector pointing at a star. It doesn't move as the Earth rotates around. And from that base point of view, we then define all the angles we needed to orient our orbit in 3D space, as well as to locate the spacecraft along the orbit. We did that through the use of 6 classical orbital elements: semi-major axis, eccentricity, inclination, Rayan, argument of perigee, and time of perigee passage. And then we saw how to practically turn those 6 classical orbital elements into position velocity at any time we desire. Practically, I'm going to say that 75% of the time, that time will be t equals 0, because we are engineers and we like to apply theory for practical things. One of them being to simulate orbits in MATLAB Simulink. Okay? And through the assignment of this course, you will have a chance to simulate orbits in MATLAB Simulink. So don't worry, you'll get to apply all this great knowledge and play with orbits and simulations quite a bit. Okay? Hope you're still enjoying the course. Hope you had a blast today. So I'll see you next time. See ya.